Hello everyone, my name's Lennard and I'm an application engineer for Rigel Medical. Today's presentation webinar and we'll go into the principles of mechanical ventilation. We'll talk about some of the terminology, the different modes with some common mode examples, and also talk about the breath cycle stages. So the start of inspiration, during the inspiration phase, end of inspiration, and also some of the triggers and cycles within ventilation. Further on from that, we'll talk about lung injuries that can potentially be caused by ventilators themselves. And towards the end of the presentation, we'll talk about the standards, ventilator testing settings. We'll talk about the analyzer setups and also some of the best practices. And then in the very final part of the presentation, we'll talk about anesthesia testing, but we only touch on that. We'll talk about that very briefly. Firstly, a little bit about ourselves at Rigel Medical. We are renowned globally as a designer and manufacturer of reliable, portable, and compact biomedical test equipment. Our products ensure that critical medical equipment is safe to use throughout the device's life cycle. As metrology specialists, for almost 4 decades, our innovative testing solutions have been mitigating risk worldwide in healthcare environments. We've got 2 operating locations. Our main manufacturing site is based in Peterlee in the UK. We've also got an office in Tampa, Florida, and that's headed up by Paul Fopel. We've got 7 global service centres distributed around the world. We've also got over 40 distribution partners covering worldwide. We're present at the moment in over 110 countries. Okay, so introduction to mechanical ventilation. Mechanical ventilation provides oxygen to patients in respiratory failure, so it's a crucial form of life support. A ventilator typically delivers air with increased oxygen content to the lungs when a patient cannot breathe on their own. So this is typically for the life support type ventilators, and the type of air that's with increased oxygen content is known as an air oxygen mix. But it's not just people on life support that need ventilation. For example, you've got portable ventilators such as CPAP machines, and they're used for conditions like sleep apnea. And here, these oxygen mixes aren't required, often just air is used. But the overall aim of a ventilator is to normalize arterial blood gases, ABG, and to aid a patient's breathing. So there are 2 primary gases that need normalizing, which I'll come on to, and those are oxygen and carbon dioxide. So you need to normalize these 2 levels within the blood. Now, ventilation can be delivered in numerous modes depending on the patient's condition. And the different modes are really important for understanding ventilator testing, and we'll come on to that, because it can affect the way trigger levels or mode should be selected on the ventilator analyzer itself. Okay, so causes and indications of ventilation. Firstly, low levels of blood oxygenation, hypoxia. This is where not enough oxygen can make it to the cells within the body that require it. Now, this is often a result of something called a VQ mismatch, when your lungs are either receiving oxygen, but there's no blood flow, so they can't transport oxygen around the body, or you've got blood flow, but you've got lack of oxygen. So there's this VQ mismatch, could be either of those 2. Now, if it's left untreated, it can lead to quite serious life-threatening conditions. Some of the symptoms become quite apparent, so skin might change colour, might start to look a bit blue. Patients as well might appear to be becoming quite confused. These are some of the real primary symptoms that can occur with hypoxia. Firstly, asthma, very common, and it occurs when lining of the airways swell, and this swelling of airways leads to narrow passageways where the patient cannot get enough oxygen into their lungs. And we've got pneumonia. This is inflammation of air sacs in the lungs. So this has become quite apparent with COVID-19. You've probably heard of it, COVID pneumonia. And this is a type of something that's known as silent hypoxia, and it's still not quite fully understood. Then we've got anemia. This is low numbers of red blood cells. Hemoglobin is responsible for binding to oxygen and then transporting the oxygen around the body to be utilised by the muscles, by the cells, by all the organs. Obviously, low levels of blood cells, that means you're going to get low or poor oxygenation saturation. Okay, you've got collapsed lungs, which ups the pressure around the lungs. I guess it doesn't need much explanation as to why you're not getting much oxygen. Then you've got acute respiratory syndrome, where you've got fluid in the sacs of the lungs. And the fluid keeps your lungs from filling with air, which means that less oxygenation is reaching your bloodstream. Then we've got hypercapnia, so this is the build-up of carbon dioxide. And this is often the result of some sort of fractured or disordered breathing. Some of the common symptoms here are drowsiness or tiredness, very similar to the symptoms you might get from some sort of blood poisoning. You also might get headaches, as well as sort of red flushed skin. Causes. Okay, so hypothermia is one, where you're getting a much higher than normal body temperature, so an abnormally high body temperature, and this can lead to an increase in carbon dioxide production. We've got sleep apnea, a disruption in breathing during sleep, and this disruption or fragmented breathing in sleep means that the body can't effectively remove the carbon dioxide in the body, and this can build up in the bloodstream. Anemia again is highlighted, so we've got low number of blood cells. As we know, hemoglobin is responsible for binding to oxygen, but also responsible for binding to carbon dioxide, so it can transport it to the lungs where it can then be expelled. Stroke is a cause, blocked blood vessels or bleeding in the brain. So in a very similar way that anemia can cause hypercapnia, so can a stroke through that blood restriction. There are also types of strokes which affect the brainstem, and that can affect the rate of breathing. Okay, so gas exchange. The two main purposes of ventilators are getting oxygen in and getting carbon dioxide out. And the way it gets oxygen in by four main processes. So increasing oxygen concentration, FiO2, mean alveoli pressure, but we don't want too much of an increase, as this can lead to lung damage. PEEP, which stands for positive end expiratory pressure. So this is keeping the airway pressure above the atmospheric pressure. And providing a higher PEEP level is what CPAP machines do. They apply a constant low pressure just above ambient pressure, and you can change those values within CPAP machines. And what it's doing is it's preventing the alveoli from collapsing. Now I've heard a good analogy on this when I was doing my research on ventilator testing on ventilators. And if you think about it like blowing up a balloon, it's always that initial resistance that makes it difficult to inflate. But once the air expands into that area, it becomes much easier. And that's how an increase in PEEP is helping the lungs. Particularly if you've got lungs that are non-compliant as well. Don't talk about compliance to the lungs, but perhaps I can touch on it now. It's where the lungs' ability to stretch and allow oxygen in. If you've got a very non-compliant lungs, they're very stiff and they don't allow to expand. So it's just one way to explain how it works. Another way of increasing oxygen is by increasing the IE ratio, usually 1 to 2. When we talk about terminology, I'll go into a bit more detail on the inspiration-expiration ratio. Now we've also got getting carbon dioxide out, and this is by means of increasing the respiratory rate, or you might know it as the breath rate, and also increasing tidal volume. So this is the total volume inspired during each breath. Here's a diagram showing how oxygen is binded to the red blood cells from the lungs. It's released into the organs. Carbon dioxide is binded back to the red blood cells and removed. Basic biology, but it explains how what ventilation is trying to improve. It's trying to get oxygen in, carbon dioxide out. Okay, so some of the so ventilators, they provide oxygen by applying volume and pressure to the patient's lungs. Now the key terms are volume, pressure, breath rate, inspiration time, exhalation time, and that will become apparent when we talk about the breath cycle. Now, this diagram shows how a ventilator uses pressure to push air, or a mixture of air and oxygen, into the patient's lungs to get oxygen into the body. So pushing, using pressure, forcing air into the lungs around the body. Already from this we can see how incorrect settings on a ventilator could cause harm to the patient, and the pressure of putting air into the lungs with a ventilator can cause damage to the lungs if the settings are wrong. Often, to keep the risk as low as possible, it's important that just the required amount of pressure is applied, but those values are for clinicians to decide. Okay, so let's talk about some of the terms. We've got IE ratio. Now this is inspiration time plus inspiration pause time to the ratio of expiration time. Now this is during a full breath cycle, which we'll come on to shortly. We've got IPAP, EPAP. This is inspiratory and expiratory positive airway pressure. IPAP is your applied pressure from the ventilator during inspiration. But what about EPAP? Is that not just PEEP? Because it's the baseline flow. In most cases it is. So PEEP is often the same as EPAP, particularly with invasive ventilation. Not necessarily with non-invasive, because the baseline pressure is not necessarily just what comes from the ventilator. Your EPAP is your applied baseline pressure. We've got trigger sensitivity. Now this is an important one. So this is what the ventilator detects as a trigger to deliver a breath to the patient. Now this comes from ventilators that provide assisted breaths, so not just from the time cycle of the ventilator, but how easy is it for the patient to trigger the ventilator to deliver a breath. Now, in general, sensitivity should be increased to improve the patient ventilator synchronization. That means to stop the patient fighting against the ventilator, to allow that sensitivity, so it's got that detection. But you also don't want it too high, which will result in like an higher triggering. So it's providing a breath when the patient doesn't want one. This comes into the triggers that are set by the patient. So when a patient wants a breath, he will breathe in, try to breathe in. The ventilator will detect this, and then will also help provide a breath. Current in assist control, which we'll talk about shortly. They've got trigger time. This is the breath detection delay before delivering a breath to the patient. If a patient has just taken a breath We don't want to instantly then provide another breath to the patient. We want to give it a certain amount of time before you then deliver another one. So the ventilator will measure the time from the end of expiration before delivering that next breath. For instance, if a respiratory rate is set to 15 breaths per minute, the flow will only be delivered after 4 seconds. End respiratory. Okay, so we've got rise time. This is the rise or speed, flow or pressure. So we can see the rise time here shooting up. That's the speed at which the flow or pressure is rising. Just explained a little bit better in this diagram. We've got the rise in pressure, how quick it's increasing. We've got peak inspiratory pressure, PIP or P peak. This is the maximum pressure in the airways at the inspiration. And we've got positive end expiratory pressure or PEEP, pressure that remains at after exhalation. Note, for invasive ventilation, it means the same EPAP. Okay, so we talk about the breath cycle. Different stages. We've got the start of inspiration. At the start, a trigger has caused the ventilator to begin inspiration. So this could be time-based. So from the respiratory rate, it's at a set rate, say every 5 seconds. The ventilator is triggering the start of inspiration, say every 4 or 5 seconds. But it could also be triggered from the patient wanting to take a breath. And this is a flow or pressure-based trigger. So the ventilator could have detected the patient wants to take a breath and a slight detection of inhalation, and then the ventilator causes another breath cycle. Then we've got 2, which is the inspiration phase, the positive airway pressure from the ventilator or IPAP. So the limit in this case is set to pressure. But your IPAP level limit, the ventilator is outputting a pressure until it reaches this limit here at the inspiration phase. Then we've got the end of inspiration. So a trigger has caused the ventilator to end inspiration and start expiration. Again, there are a few variables that can trigger the cycle to end. So if we're talking about the most common type in ventilation, tidal volume. If we say that 500 mils of tidal volume is set in the ventilator, once 500 mils been delivered during the inspiration phase, then the end of inspiration has been triggered. So we're outputting pressure. We've got 100 mil, 200 mil, 300 mil, 400 mil, 500 mil has been delivered. Now we can begin the expiration from the ventilator. Now it might not necessarily be volume. The cycle could be something different. It could be pressure. So as the pressure's increased to a certain value, okay, we've reached the peak pressure that we've got the ventilator set to. Now we can start the end of inspiration. But this is a typical ventilator setting to use in volume. Now we've got baseline. The baseline is the phase between the breath cycle. PEEP is the positive pressure that remains in the air. So this pressure support here is the positive airway pressure from the ventilator. There's always going to be some baseline pressure within the air, right above this floor. Okay, so a bit more about the breath cycle. So let's say a respiratory rate of 20. That means 20 breaths every minute. The total breath cycle time equals 3 seconds for this particular breath setting. So 60 divided by 3, you're going to get 20 breaths. Now, if we were to set an IE ratio of 1 to 2, that means we've got 1 second inspiration time and a 2 second expiration time. Pretty simple. Now, if you remember from the terms, inspiration time plus inspiration pause. Important to remember for these breath cycles. Also, volume is the amount of air delivered for a breath cycle. We've already established. That explains the IE ratio a little bit better. Okay, so we talk about some of the ventilator modes. Okay, so in life support ventilation, there are two breath types, and we've got controlled breath and assisted breath. All respiratory work is done by the ventilator with a controlled breath, and it does this by creating positive pressure to drive the tidal volume into the lungs. Muscles remain passive, so all the work is being done completely by the ventilator. Important things like anesthesia, so whereby the muscles in the body are not necessarily working correctly during anesthesia, so we need that controlled breath. Then we've got assisted breath, so respiratory work is shared by the muscles and the ventilator. Controlled breath, but a patient may also trigger a breath. And the key factor is the trigger. So some examples. Controlled breath. So one example here is a volume control, which I spoke about in the breath cycle. 500 mils of tidal volume. We use that last example. Each breath cycle receives 500 mils of tidal volume. The trigger variable is set by the respiratory rate, so your breath per minute. It's a mode that is set. The ventilator is in full control. It needs to output 500 mils of air every so many seconds. So it's very simple. Assist control in assisted breath is another common example. So you've got your mandatory breaths per minute, like with the volume, but we also spoke about the trigger sensitivity. So what the ventilator takes as the trigger for delivering a breath or pressure support to the patient. So if a patient tries to take in a breath, the ventilator will then deliver an additional breath at a set value. And here's some of the common mode examples. Volume control, patient receives the same breath with the same parameters set by the ventilator. Assist control, the patient receives the same breath with the same parameters set by the ventilator. However, the patient may also trigger a breath when required. Then we've got pressure support. So this is another type of assisted breath. The patient receives a constant pressure as well as a further pressure when the ventilator breath pressure is triggered. And then we've got continuous positive airway pressure, CPAP. And this is another example of assisted breath. The patient receives constant pressure throughout the respiratory cycle, but they're breathing on their own. Okay, so I spoke a lot about triggers, but not really explained how it works. Once you get an understanding of how triggers work in ventilators, it helps you understand how triggers work in ventilator analyzers. They're very different in some ways, but it gives you a good understanding of triggers in flow pressure. So what causes the start of inspiration, end of expiration? So there's three variables: pressure, time, and volume. So for example, in volume control mode, the cycle is the volume and the limit is the flow, but the time is the trigger. In assist control mode, the cycle is the volume and the limit is the flow, but the trigger is time, as well as flow or volume from the patient. So we've got the same cycle and same limit in these modes. So the cycle is the volume. That's where we end our expiration. The limit is the flow. So the upper limit is the flow, but it could also be the pressure. So your limit here could be pressure. And then the trigger is either time or it's the trigger from the patient, which is the flow or volume. So that expiratory phase in the pressure control ventilation would be when the pressure threshold has been reached. So a slightly different cycle example. We know that once the cycle has reached a full volume of 500 mils, then the end of inspiration begins. But in a pressure controlled ventilator mode, the cycle would be into the expiratory phase once the pressure threshold has been. Okay, so some of the problems associated with mechanical ventilation. There are several problems associated with ventilators that have potentially long-term health effects and include atelic trauma, I think that's how you pronounce it. This is damage caused by repeated alveoli collapse and expansion. So if you imagine the respiration rate of a ventilator was performing inaccurately, damage of this form could occur. So if the respiratory rate was higher than it should be, then it could cause this type of damage. Then you've got volutrauma. This is damage caused by normal alveoli, local overdistension, leading to rupture. So for instance, if a ventilator pressure value was higher than its set value, this could lead to volutrauma. Then you've got biotrauma. This is damage as a consequence of a patient's severe inflammatory response to being on a ventilator for long periods of time. This highlights why ventilators need to be performing accurately. Of course, many of these injuries could be caused by user error and putting the wrong values or undiagnosed conditions, but having ventilators perform accurately is crucial. So correct levels of parameters such as PEEP, inspiration volume ensure that the effects of VILI are reduced. Modern day ventilators are equipped with a variety of alarms such as low oxygen pressure and insufficient volume delivery. Valuable only if the parameters of the ventilator are accurate. Regular performance testing ensures the ventilator parameters are within specification. Now we go on to ventilator testing. IEC 80601-2-12, particular requirements for the safety of lung ventilators. Now this is critical care ventilators. It's an internationally recognized standard. It covers the performance and usability requirements of critical care ventilators only. It does not apply to your portable ventilators like CPAP machines or high frequency oscillation ventilators. It's only for your critical care. Performance and testing recommendations in the standards, but always follow the service manual of the device under test. Always the manufacturer recommendation. But we can establish a typical PM schedule. This is performing visual inspection. Want to check for damage to equipment, tubing or cabling. We carry out an electrical safety test, either to IEC 60601, IEC 62353, or your local national code or standard. We ensure that the equipment is clean and decontaminated. It's very crucial for ventilators due to cross-contamination. This is things like replacing filters. That also is very important for ventilators, just ensuring that the entire mechanical circuit clean and decontaminated. Also replacing components recommended by the manufacturer. And then we'll come on to performance testing. Okay, so measurements are specified by the manufacturer. Standard measurements during performance tests are flow and pressure. There are often other parameters that need to be tested, such as PEEP, IE ratio, and tidal volume. The gas flow analyzer must reliably detect the ventilation's breath cycle, so the settings are crucial. The analyzer also needs to know the gas type and standard. I'll come onto in the next few slides. Okay, so ventilator analyzer settings. Okay, so trigger settings. Here, breath detection is crucial. We need to establish where the starting point for the start of the inspiration cycle, and also where the end of expiration is. Now, they're used to identify the start and end measurements and these specific points in the breath cycle. The start and stop trigger must be high enough to be above any noise, but low enough for accurate measurements. It needs to be above this noise floor. We don't want to be detecting any noise as a breath, but it needs to still be low enough for accurate measurements. As you can see here, triggers set too high, then it can lead to an incorrect volume during inspiration and inspiration time. The inspiration time is too short because the trigger is set too high. It makes the cycle time shorter than what it actually is. And because of the calculation of volume, the volume will also be much less than what is actually produced by the ventilator. Okay, so ventilators can often trigger on flow or pressure, so you've got a choice of one or the other. The moment of the flow or pressure signal reaches the set level, the trigger is then activated. The moment that this happens, the measurement takes place. Different start and end trigger levels can be set in the vent test. In this example, the start and end trigger are set for flow. So 3 litres per minute and minus 3 litres per minute typically set as standard for adult ventilation. And here we've got the start and end points at this point of the rising time, so you're capturing everything within the breath cycle. But you could also set it on the pressure. So if the pressure was set for the trigger, then you can use that as well with most ventilator analyzers. Now, if a trigger occurs on a spike, a false breath could be detected. So here's an example where you've got a spike or a noise, I guess a noise spike, and then a false breath could be measured at this point here. What we've got is a trigger delay, and this avoids false triggering due to noise or spikes in a measured signal. The trigger will be ignored if the signal returns below the trigger within the set delay. Once a delay has passed, an analyzer will still measure the signal from the start point. There's a set time value which needs to be exceeded to count as an actual breath. Any short bursts of noise, which can occur in ventilators due to switching mechanisms, etc., they can then simply just be ignored. They're established as noise or spikes, and the actual breath is measured rather than the noise spike. Again, this ensures accurate measurements through breath detection. How does an incorrect trigger affect volume integration and measurement? Well, tidal volume is determined by integrating the area under the flow curve. This means that with a trigger set too high, not only is the flow at the start of inspiration completely omitted, the negative flow also subtracted at the end trigger. Now, our ventilator analyzers have preset triggers for particular modes, so some manual triggers may not need to be set in most cases. But if you do require manual triggers, then the Flow Lab software that goes with the vent test is often preferred, as you can visualize these waveforms and change the triggers accordingly on screen to capture the waveform. And here is how the calculation of tidal volume occurs. So this is why subtraction occurs at the end of the measurement if the trigger is set too high. Okay, so setting the gas type and standard, why this is important. Now, you always need to make sure the gas and standard match the device under test. You've got to ensure that the gas type, gas standard matches the actual gas flow you're measuring. Very important due to the different characteristics between gases, such as viscosity and density. Incorrect settings lead to inaccurate measurements, and it can be as high as 20% inaccuracy. And the table shows that it's important even at ambient temperature that the correct conditions are set. Whether there's high humidity or dry conditions, this can also affect the accuracy of the measurement due to the characteristics of gases, different temperatures and in different conditions. Okay, so brief overview of the measurement setup, or a typical measurement setup of the ventilator. This is a typical measurement setup. The ventilator and test lung, they're effectively simulating the patient. The ventilator tester verifies the settings and the monitoring system of the medical mechanical ventilator. And it does this measuring the breath-based parameters using the test lung. So this could typically be seen in hospitals, service departments, manufacturing, research and development, all types of settings for testing a ventilator. And what you might see with some manufacturers of the portable type ventilators, CPAP machines, etc. The service mode might just state a flow rate of 100 litres per minute. So it might just stipulate a set flow and pressure, and you just need to measure that flow or pressure using the vent test. And this is done by simply removing the test lung, because you're not measuring any actual breath-based parameters. You're just measuring flow through the device or pressure. So that's another setup that you might see for some of the home care type ventilators, not the critical care. Okay, so this relates to some of the best practices. Now with the vent test, it has a long inlet, so turbulence is not a major factor. It's still recommended that the inlet is not curved or bent before entry, so tubing should be straight before being connected to the inlet of the vent test, as this can induce turbulent flow and it can affect the accuracy. Now, a longer, straighter tubing before the inlet ensures laminar flow, and it's certainly recommended for the handheld Citrix type testers, which do not have long, straight tubing before it gets to the measurement. So here's an example with the vent test. You've got this long tubing with the air filter here as well. That allows for the flow to become laminar before being measured. Whereas differential pressure sensors are in something like the Citrix, you might have turbulent flow coming in here, and it will affect the measurement because it needs laminar flow for higher accuracy. And we do sell straight tubing for the Citrix range or the vent test if required. So this helps produce laminar flow. Okay, so setting the trigger on the vent test. And we know that the trigger must be set above the baseline for the noise. Now we need to set the settings in the ventilator analyzer, but it has preset settings, which will cover most of your ventilator testing needs. There are 3 preset trigger modes: you've got adult, pediatric, and high frequency oscillation. Individual signal sources for start and stop conditions. You can have an external trigger. We've got important to select the correct setting if you need to measure ventilator parameters, e.g. PEEP, inspiratory volumes, inspiratory times. And then to set manual triggers, FurLab is favourable due to the on-screen real-time measurement. Now each ventilation mode here, we've got the 3 different types of triggers. These are related to a standard set of triggers. If you do change them to a custom trigger level, then you can always just reset them to come back to these standards. That's always an option, but you can adjust them to be manually triggered. Adult ventilation, these measurements typically measured in the high flow channel, as well as high frequency oscillation, whereas the pediatric measurements will typically be taken through the low flow channel. Now, in the next webinar where we talk about the vent test, talk about the inlet and the outlet of the low flow and the high flow channel. So you you actually reconnect the low flow channel to the high flow channel to get more of the breath-based parameters, because it's only the high flow channel that measures O2. But if you are interested in the function of the VenTest 800, then just sign up to our next webinar, and I'll go into a lot more detail on the setup for each type of test. And then at the end, we'll just briefly talk on anesthesia testing. Okay, so this is a very simplified circuit for an anesthesia machine, but it will provide an overview into how machines work. Okay, so a ventilator is included in the circuit for respiration. There's a vaporizer, and this produces an anesthetic agent to the patient from the supplied gas. Now, it works by producing an agent from liquid. So you've got agents that are within the vaporizer, and they're mixed with the gas supply, the input gas supply that's flowing in. Now, the design of these vaporizer devices takes into account of varying conditions, such as the ambient temperature. So it needs to have all the correct settings to correctly vaporize these types of gases. And they can include halothane, influrane, isoflurane, sevoflurane, and desflurane. And so these are added to the gas supplies, such as you might have nitrous oxide, pure oxygen, or just air coming in through the system. The vaporizer must produce an accurate, controlled level of these gases to the patient. So we're introducing new parameters to be measured with the ventilator. We're not just talking about the ventilator anymore. We're adding different factors where it's important that there's controlled, accurate levels of these anesthetic agents. And we have this device here, which goes with the vent test, and this is what's used to measure concentrations of those anesthetic gases. It gives you instant gas concentration measurements, fast response time without stabilization. It's compatible with all anesthetic gas types, all of these types here, capable of measuring, as well as the gases such as CO2 and nitrous oxide. It's battery powered, compact, and it's lightweight housing. So it's just a small adapter, connects to the front of the VenTest 800. It goes over there, and then it detects the different gas concentrations and displays these on the statistics screen with the breath-based parameters. So it's a way of also testing your anesthesia machines. And that brings us to the end of today's presentation. Only briefly touched on anesthesia testing. If you think it's valuable that we could expand on that a little bit more, then I will. But today I just wanted to go mainly into ventilator testing, as that was the core principles of this webinar. If you've got any questions, pop them in the question box below. I will make these slides available, so in a PDF format in the handout section below as well. You should be able to download these, but if you're not able to, again, just let me know in the question box, and I can send these over to you via email. Thank you again for viewing today's webinar. If you're interested in the vent test one, that's in a couple of weeks' time. Check our events page at rigelmedical.com. But for now, thank you again for viewing this webinar. Hope it was useful. I'll tell you what else I'll add to the end is a feedback form, just so you can help us how we can improve on our presentations, what we're doing right, what we're doing wrong, and how we could do better. It's always good to hear feedback from you guys. But for now, I'll just go through some of your questions. Okay, thank you.